Hello student, I am Assistant Professor Mangesh Jamdhade working in a physics department of S.V.K.T College, Devlali camp. We are studying the lectures on the atomic physics. In the last lecture, we have studied about how to write the spectral notations of various quantum states, and we have also solved some examples based on the spectral notations. Now, in today's lecture, we will start the concept of spin-orbit interaction. But before going to that concept, we have to study the fundamental required for that concept. So here we will study some basic fundamental concepts, which are the magnetic moments of atom and the Larmor precision. So in the today's lecture, our learning objectives will be to understand the basic concepts required for spin-orbit interaction and to understand the orbital and spin magnetic moments of an electron. Also to understand the Larmor precision and to find the formulae for Larmor frequency. So let's start with magnetic moment. Now we already know that whenever any circular loop is there which is carrying a current I, and suppose this circular loop has a radius r as shown in the figure. So its area is A, circular area of the loop is A, then the magnetic moment associated with this circular loop is the product of the current through the loop and the area of the loop, and it is a vector quantity. The direction of the magnetic moment of circular loop is normal to the area, is normal to the plane in which the loop is there. So it is parallel to the area vector A bar. So the direction of mu bar, magnetic dipole moment, and the A bar is the same. So mu bar equals to I A bar, or in magnitude mu equals to I times A. Here A is the area of the loop. So similarly here, whenever we consider the Bohrs atomic theory, we know that the electron is revolving in a circular orbit around the nucleus, and electron is a charged particle having a negative charge of -e. So it constitutes a current loop, and the current is I here. So current is given by charge per unit time, and so in magnitude I will be equals to E divided by T. Here E is the charge on an electron and T is the periodic time of electron, that is time the electron takes for one complete revolution in that orbit. And so we know that the periodic time is given by T equals to 2 pi r divided by V. Here 2 pi r is the circumference of that orbit, and V is the velocity of electron in that orbit. And so the periodic time, if I insert that time in the equation of the current, I will get I equals to E times V divided by 2 pi r. Here r is the radius of that orbit. And we know that from the formula of magnetic moment, mu equals to I times A. So mu will be equals to I is here EV by 2 pi r, and the area of the circular loop having radius r is pi r square, and so you will get mu equals to EVR by 2. I will lose my pi and one r there, so I will remain with mu equals to EVR by 2. So let me multiply the numerator and denominator of this equation by mass of an electron m. So if I multiply here by mass of an electron, I will get mu equals to E times mvr divided by 2m. Here mvr is nothing but the angular momentum of electron in that orbit. So L equals to mvr. And so I can substitute, instead of mvr, I will write there mu equals to EL divided by 2m. So this is the magnitude of the magnetic moment of an electron. And vectorially I can write this magnetic moment as mu bar equals to minus E divided by 2m into L bar. Here the negative sign is due to the negative charge on an electron, and so you can observe that the magnetic moment of an electron is opposite to the angular momentum vector L bar. So they are oppositely directed as shown in the figure. And here this magnetic moment is due to the orbital motion of an electron in an orbit, and that's why it is called as the orbital magnetic moment. And it is given by mu L bar equals to minus GL E divided by 2m into L bar. So here the factor GL is called as the orbital G factor, and its value is experimentally it is 1, and so mu L bar equals to minus GL E upon 2m into L bar. Here magnitude wise I can write the orbital magnetic moment as mu L equals to minus GL into E by 2m into L. So the ratio of the magnetic moment, that is orbital magnetic moment, to the orbital angular momentum, that is mu L divided by L, will be E upon 2m. If I substitute GL equals to 1, I will get mu L divided by L is E upon 2m, and this ratio is known as the gyromagnetic ratio for orbital motion. So for orbital motion, gyromagnetic ratio is E upon 2m. E is the charge on an electron and m is the mass of an electron. We also know from the quantum theory that the orbital angular momentum, magnitude of the orbital angular momentum is given by square root of L into L plus 1 h cross. Here small l is the orbital angular momentum quantum number, or simply orbital quantum number. And if I substitute that value in the above equation of the magnetic moment, I will get mu L equals to minus GL E h cross upon 2m into square root of L into L plus 1. And here you will observe one factor E h cross upon 2m. That factor is the elementary unit for the magnitude of the magnetic moment of an electron, and it is known as the Bohrs magneton. So EH cross upon 2m is the Bohrs magneton, and its value is mu b equals to EH cross upon 2m. If you calculate that value by substituting the values of all other fundamental constants, you will get mu b equals to 9.273 into 10 raised to minus 24 ampere meter square. The unit of this mu b is same as the mu L, that is magnetic moment. So it is a fundamental magnetic moment associated with the electron due to the orbital motion. So mu b equals to 9.273 into 10 raised to minus 24 ampere meter square in SI unit. And that's why I will get mu L equals to minus GL mu b, let me multiply and divide it by h cross square root of L into L plus 1 into h cross, and that will simply mu L equals to minus GL mu b upon h cross into L. So here you cannot directly measure the L, you can only measure the Z component of L, that is Lz, and we know that the Z component of L that is Lz, which is given by ml h cross. Here ml is the orbital magnetic moment quantum number. So Lz will be ml h cross, and also you can measure the Z component of the magnetic dipole moment, which is a mu Lz. So mu Lz will be equals to minus GL mu b upon h cross into Lz. If I substitute the value of Lz, I will get mu Lz equals to minus GL ml into mu b. So here we have the formula for the magnitude of the orbital magnetic moment and for the Z component of the orbital magnetic moment. Now similar to the orbital motion, the electron has one more motion called as a spin motion. The spin is the intrinsic property of the atom, and due to that the electron has a spin angular momentum S bar. Now in analogy with the orbital motion, we can directly write the formula for the orbital spin magnetic dipole moment. So we have here orbital magnetic dipole moment given by mu L bar equals to minus GL E upon 2m into L bar. Similar to that, we have here mu S bar, which is the magnetic dipole moment due to the spin motion of an electron, is mu S bar equals to minus GS into E upon 2m into S bar. Here S bar is the spin angular momentum and mu S bar is the magnetic dipole moment due to the spin, and you can observe that they are both opposite to each other as shown in the figure. The negative sign indicates that. Here the factor Gs is called as the G factor for spin and its value is 2. Experimentally its value is 2 approximately. So you will get mu S equals to minus Gs E upon 2m into S bar. Or in magnitude wise, I can write that as a mu S equals to minus Gs E upon 2m into S. Here also the ratio of the magnetic dipole moment for spin motion to the spin angular momentum is equals to E by m. It is called as the gyromagnetic ratio for the spin motion, and you can observe that the gyromagnetic ratio for the spin motion is double than the gyromagnetic ratio for the orbital motion, because for the orbital motion this ratio was E divided by 2m, and for spin motion it is E divided by m, so it is double for the spin motion. Also we know that from the quantum theory that the spin angular momentum magnitude of the electron is given by square root of small s s plus 1 h cross. Here small s is the spin quantum number, and for the electron the spin quantum number is 1/2. Small s equals to 1/2, and by substituting that value of spin angular momentum I will get mu s equals to minus gs into eh cross by 2m into square root of s into s plus 1, and we already know that this quantity eh cross upon 2m is the Bohrs magneton. So I will get mu s equals to minus gs into mu b by h cross into s. So this is the magnitude of the spin magnetic dipole moment of an electron, and it is given by mu s equals to minus gs mu b by h cross into s. Similarly here also you cannot directly measure the spin of an electron. You can measure its z component, which is given by mu s z, that is equals to minus gs mu b upon h cross into sz. So here also you can measure the z component of the magnetic dipole moment. Now sz value is ms h cross, where ms is the magnetic spin quantum number and it has a value from minus s to plus s. So you will get mu sz equals to minus gs ms mu b. So here also we have the formula for mu s spin magnetic dipole moment, which is gs minus gs mu b by h cross into s vectorially, and mu sz, which is the z component of the spin magnetic dipole moment, which is minus gs ms into mu b. Now let's study about the Larmor precision. The precision of the angular momentum vector and the spin angular momentum vector in presence of the external magnetic field, how that occurs. Now we know that an electron is moving in the nucleus around the atom is equivalent to magnetic dipole. We have also find its value for the magnetic dipole moment, both for the spin and orbital motion, and hence whenever you place an electron in an external magnetic field as shown in the figure, the electron orbit will precess about the field direction. So the electron orbit start precessing about the field direction, that is externally applied magnetic field direction, and this precession is called as the Larmor precession, and this precession has some frequency which is known as the Larmor frequency. So here you can observe that we have shown the orbital angular momentum vector L bar, and mu L bar is oppositely directed to the L bar. As you place this atom in external magnetic field, the magnetic moment mu L bar will experience a torque, which is given by tau bar equals to mu L bar cross B bar, and its value will be tau equals to mu L bar cross B bar. Its magnitude will be tau equals to mu L B sin theta. Here theta is the angle between L bar and B bar. So the angle between mu L bar and B bar will be pi minus theta, as you can observe in the diagram, and the sine of pi minus theta is same as the sine of theta. So you will get tau equals to mu L B sin theta. This is the torque experienced by the magnetic dipole moment mu L. and due to that torque, you can observe in the diagram the torque has the direction which is perpendicular to the mu L and B both, and so this torque will change the angular momentum of an electron according to Newton's law. So tau will be equals to dl by dt, or I can write delta L by delta t. So torque will change the direction of the angular momentum. It will not change the direction magnitude of the angular momentum, but it will change the direction of the angular momentum. And due to that change, I can write delta L from the figure. As you can observe from the figure, delta L is a L sin theta into delta phi. Here L is the angular momentum, and the component L sin theta is opposite to the theta, where theta is the angle between L and B. So delta L will be L sin theta delta phi. So in time delta t, the direction is changed by the amount delta phi. So you will get tau equals to L sin theta delta phi by delta t, because tau equal to delta L by delta t, and delta L is nothing but the L sin theta delta phi. So tau equal to L sin theta delta phi by delta t. Delta phi by delta t is the nothing but the change in angle with time. That is, it is angular velocity omega, angular displacement by time, which is angular velocity omega, and this omega is nothing but the frequency of precession of the orbit, which is known as the Larmor frequency. So you will get tau equal to L sin theta omega. Now you can observe equation 1 and equation 2. Equation 1 gives you the torque experienced by the mu L, which is mu L B sin theta, when it is placed in an external magnetic field, and equation 2 gives you the torque on an torque which changes the angular momentum, which is L sin theta omega. So if you compare these two equations, you will get mu L B sin theta equals to L sin theta omega. I will lose my sin theta, and I will get omega equals to mu L B by L. So omega is the angular frequency of precession, which is mu L B by L, and we already know that mu L value is E by 2m into L. If I substitute this value of magnetic dipole moment in this equation, I will get omega equals to EB by 2m. Here E is the charge on an electron, B is the magnitude of the external magnetic field, and m is the mass of an electron. So here omega is the orbital Larmor frequency of the orbital motion for an electron. So it is actually the Larmor frequency of the precession of angular momentum vector. Similarly, for the spin motion also, as you can observe from the figure, spin angular momentum is also precesses around the magnetic field, and the angular velocity of the precession is given by omega equals to mu s into b divided by s. So here mu s is E by m, and you will get omega equals to EB by m. So I will lose my s here. So finally you will get omega equal to EB by m. So EB by m is the Larmor frequency of precession for the spin vector. So for the angular momentum vector, orbital angular momentum vector, it is EB by 2m, and for the spin angular momentum vector, it is EB by m. So you can observe that the Larmor frequency for the spin angular momentum vector is a double than the orbital angular momentum vector. Okay, so this is a fundamental required for the spin orbit interaction. Now in this lecture, student have to solve these two assignments. So first, student have to define magnetic moment. What is magnetic moment? And you have to write the formula also. And also student have to define the Larmor frequency and write the formula for both spin angular momentum and for the orbital angular momentum. Now let's quickly go through the summary. In the today's lecture, we studied about the magnetic moment is the product of the current through the loop and area of the loop, and its unit can be seen from this formula, which is ampere meter square. Also, the orbital magnetic moment of an electron is given by mu L bar equals to minus GL upon into E upon 2m into L bar. So here GL is the orbital g factor, and its value is 1. Similarly, for spin motion, mu s equal to minus gs e upon 2m into s bar. Here gs is called a spin g factor, its value is 2. And the Larmor frequency for precession of orbital angular momentum is mu l b upon L. Okay, in the upcoming lecture, we will study in detail about the spin orbit interaction.